week. It's beautiful outside. I hope you get outside for a lovely walk. The colors are just starting to change and it looks beautiful. The OWL Admin Matters quiz was due yesterday. It has that 48-hour window, so make sure you get that in if you haven't done so already. We have the first team module now available on OWL. So if you go to Content and scroll down to Team Problem Solving Modules, you can find the first Topic 2.1 module. We encourage you to work with a team. So you can find your own friends or teammates that you want to work with. They could be in this section. They could be in another section of Chem 1301A. You can meet in a residence. You can meet in a library. You can meet on Zoom. You can meet at a cafe. You can meet in the resource room. Wherever you like. These modules have been designed by undergraduate and graduate students and myself to guide you through discussion of these important topics. So you'll notice in your workbook that we have in-class examples, and we'll start going through some of those today. Some of them say in-class, and some of them say team. When it says team, those are the ones that show up in the team modules. But the team modules cover even more than that. We have online simulations. So here are some example ones from topic 2.1, where you can visualize orbitals. You can look at wave behavior and change the frequency and change the intensity of the wave. You can discuss different concepts and definitions and applications. We also have career connections. You can meet people who have graduated from a chemistry program and see what cool career they're working in. Or you get to meet some of our graduate students doing cool research that connects to first-year chemistry topics. So over the term, you'll have different interviews in these modules as well. So you can find your own team, or if you want to meet some new people, you can go to OWL Communications, Groups, and sign up for a team there. We strongly encourage you to complete this module prior to test 1. So you know the first weekend in October, we have our first test. It's nothing to stress about yet, but you want to start preparing. That means getting through that self-study material by the end of September. We have some self-study modules that are already available on OWL. Who's opened those self-study modules? Okay, so many of you, that's great. We encourage you to work through those as you move through the Chapter 1 material. And then once we get to Chapter 2, that's when those team modules are graded. That's when they officially turn into team modules. You can do them individually if you need to, but we really encourage you to work as a team. Teaching the concepts to one another is how you're going to learn better. So for these team modules, make sure that you complete them in your own OWL account. So navigate through them. And there's also a little completion quiz, it's short and sweet, but that's how we track your completion grade as well. Any questions about the modules? Okay, so we'll be releasing those throughout the term, and we hope you really enjoy them. Okay, this is a thumbs up question, so this isn't quite an eye clicker question yet, but electrons are best understood as, we're going to go by show of hands. Who says highly suspicious? B, waves. C, particles. D, photons. E, waves and particles. Okay, and everyone chose that. Well done. Electrons have particle behavior. It's like a little particle. It has a mass. It can be transferred, but electrons can also be understood as waves. And this was a revolutionary idea. This blew people's minds that matter, like stuff, could also behave like a wave. Well, we need to learn a little bit about waves, as we did last class, and you've learned in physics, some properties about waves that also apply to electrons. The first two are that electrons can produce a diffraction pattern. So they expand to fill up the space, kind of like light does. And electrons can produce an interference pattern. So if we have electrons going through one little slit and another electron beam going through another split, they can undergo constructive and destructive interference, depending on how we add the maxima and the minima. So they can amplify one another, the amplitude can get higher, or they can kind of cancel each other out if they're completely out of sync. Waves can do that, and electrons can do that as well. Waves can have nodes. And when we're talking about standing waves, we introduced that concept last week, where they have an anchor point. So traveling waves, just you drop a rock in the water and it travels outwards. We're talking about standing waves, where we have that anchor point, and we brought that slinky last class, where it was anchored, and there are certain allowed states and certain not allowed states. So we saw how the slinky could go up and down in a regular motion, kind of like a guitar string if you've played guitar. And it could have no nodes, just going up and down. Or it could have a steady state with one node oscillating, positive phase, negative phase, but having one node. You can't have half a node. That's not going to be stable and continue. But we can have 0 nodes, or 1 node, or 2 nodes, or 3 nodes. And as the energy increases, the number of nodes increases. And we're going to see electrons follow this behavior as well. We're going to see today that orbitals, ways that we can describe where the electron could be found, also have nodes. We're going to see that orbitals can interact constructively and destructively. We're going to have to wait a few topics to get there, but we can actually combine electrons in orbitals, and this is how bonding occurs. And these properties of waves inform that. We're going to see that electrons can be found in certain places and cannot be found in certain places. There are going to be nodes, regions where we won't find those electrons, kind of like waves. So this Schrödinger equation that's shown on the screen is a way to convey the energy and kind of information about the location of that electron. We have the wave function, that little psi on both sides of this wave function. We can talk about the wave function here and talk about the wave function here, and we have a way to connect energy to where that electron could be found. We take the square of that wave function, to take that psi, square it, and we get the probability of where that electron could be found. The left-hand side of this equation is called like the Hamiltonian operator. We can see we're doing like a second-order derivative there. We have pi, we have the mass of the particle, we have h squared, h is Planck's constant, and thankfully, we're not going to be solving this equation. This equation has been solved, and there are multiple solutions. Today, we're going to look at what those solutions are and interpret what these solutions mean. So, electrons can behave like waves. They have wave-like properties. When we think of electrons as waves, we can use this Schrödinger equation and analyze the solutions. Okay, so now we're going to look at how we can interpret what these solutions are. In one way, we can solve for these solutions, and we can come up with the emission spectrum of hydrogen and those waves or those photons that are emitted, and it matches. So it makes sense. But now we're going to look at the multiple solutions and see what they mean and take it from there. So solving Schrödinger's equation, we get 3 quantum numbers plus 1. So we have 4 quantum numbers that can describe the behavior of an electron. 3 of these quantum numbers describe the orbital. So we've already seen that we can talk about an electron as a wave function. The wave function shows up in Schrödinger's equation. When we learn about this wave function, when we solve Schrödinger's equation, we get quantum numbers. The first 3 give us information about the orbital. Tells us the size. When we square it, we get the probability of where this electron could be found. So each electron in a molecule or in an atom is going to have its own unique 4 quantum numbers. As you already know, we can fit 2 electrons in one orbital, and the first 3 quantum numbers here tell us about that orbital. The first is the principal quantum number, and we're going to go through each of these in more detail. This is just kind of the big overview first. The principal, the first one, is giving us the big idea of size and the big idea of energy. The second, that L, or azimuthal, or angular orbital momentum, that's when we learn about its shape. Then we're going to get to the magnetic quantum number, M with that little subscript L. It lets us know about the orientation of that orbital. Those three quantum numbers tell us about the orbital. Then the final differentiates between the two electrons in that orbital. So let's go through each of these quantum numbers because we want to interpret the solutions to Schrödinger's equation. So the first, the principal quantum number, N. When we know what this is, we have a general idea of the overall size of the orbital and the overall energy of the orbital. So if we look at these different standing wave functions, these are simply in one dimension. We're only looking along the x-axis. But orbitals exist in three dimensions, x and y and z. And towards the latter part of today's lecture, we're going to see how these numbers make sense in three dimensions. We're going to look at the pictures later on. We're starting with the quantum numbers and the rules. So the principal quantum number, it has some very specific rules for what's allowed and what's not allowed. The principal quantum number must be a positive integer. That means it can't be negative, like -2, and it can't be a fraction, like 1/3. It could be 1 or 2 or 3 or 4 and it keeps going up. As long as it follows those rules, then that would be a permitted quantum number. So if we look at these standing wave functions here, this could be n equals 1, n equals 2, n equals 3, and we could keep going. As the principal quantum number gets bigger, the energy of that orbital increases, and the size of that orbital increases as well. If we know what n is, that principal quantum number, we can very quickly calculate the number of nodes, the number of planes or spheres or regions of space that the electron will not be found in that orbital. If n equals 1, well, the number of nodes is n minus 1. So if n equals 1, the number of nodes is going to be 0. If n equals 2, well, 2 minus 1 is 1. It will have 1 node. So as soon as you know the principal quantum number, you can very quickly calculate the number of nodes. And moving on in today's lecture, we're going to visualize and see what this looks like in three-dimensional space. So the second quantum number, the second important piece of information about an orbital is L, the azimuthal quantum number, or the angular momentum quantum number. And this gives us a good idea of the shape. And each of these L quantum numbers coincides with a particular shape. L also has its own set of rules for permitted quantum numbers. L has a few options, and it depends on what n is. L is allowed to go from 0 all the way up by integers to n minus 1. So let's start at the bottom of this table. If n equals 1, well, what are the options for L, that second quantum number? It can go from 0, so 0 is an option, all the way up to n minus 1. 1 minus 1 is 0. So it can be 0, or, well, just 0. So L could be 0 if n equals 1. Why do we care? What does that mean? How do we interpret that? As soon as we know that L equals 1, we know that we're talking about an s orbital. So if L equals 0, I hope I said 0, then we're talking about s. If L equals 1, we're talking about p. 2 is d. 3 is f. I like to count with my fist. I start counting at 0. This is probably the most common error for this particular topic, starting to count at 1 instead of 0. So S, P, D, F. You count out starting with your fist at 0. S is 0, P is 1, D is 2, F is 3. So let's now move over to if n equals 2, based on our rules, what are our options? Well, if n equals 2, L, that azimuthal second quantum number, it can be 0 all the way up to n minus 1. So 0 is an option. 2 minus 1 is 1. So 1 is also an option. So the principal quantum number is 2. If L equals 0, well then we're talking about 2s. If L equals 1, we count up, sp, well then we must be talking about a p orbital. We can keep going. As you can see, if n equals 3, well L is allowed to go from 0 all the way up to n minus 1. So it could be 0 or 1 or 2. And we could continue on that way. So make sure you learn the order of S, P, D, F, kind of becomes a little rhyme, and how to go back and forth between L equals whatever number to S, P, D, F. Who remembers S, P, D, F from high school? Okay, excellent. So you might already be visualizing what S, P, D, F means. We're going to get to that. It's coming up and it's going to come together. Until then, we're going to move along with our quantum number rules. Okay, based on our quantum number rules thus far, which orbital does not exist? When we talk about quantum numbers, we have rules for what's allowed and what's not allowed. Kind of like springs. They can have 0 nodes or 1 node or 2 node. They have allowed states. We have allowed numbers and not allowed. Chat with the person beside you and submit your answer.
Wonderful clicker. Is there a new one, or I can just use this again?
You need to add my section. So add a new course, search Western University, Ontario, type in Chem, C-H-E-M.
C-H-E-M.
There you go. And then this is the 130, and I'm Christina Booker. So this is what you want to add.
Okay.
There you go. Add that course, and we have launched this.
Yeah, so I use like things here, so it's gonna be also be counted, right? So it won't be like a losing marks.
We round up at the end of the term, as long as you meet 70% of the questions.
So it makes it both of it, right?
No, you only get points for the section you're enrolled in moving forward, but we have lots of questions we'll ask during the term.
And we're all talking about the same thing, right? Teaching the
We are, yeah. And 10 more seconds. And 3, 2, and 1. Okay, 91% went for B, and I agree. This one is not allowed. Why? Well, in this orbital, n equals 2, that's fine. That's a positive integer. But based on what's written here, we count up from 0, S, P, D, F. That means L equals, wait, I just counted, S, P, D, F, L equals 3. Well, L is allowed to go from 0 all the way up to n minus 1. So if n is 2, L could be 0 or 1, and that's it. L equals 3 is not a valid option. Therefore, this orbital does not exist. Now we need to learn the rules, but then we're going to see why this makes sense. Did I make a typo? Go ahead. S, P, D. Thank you. Yes, I totally miscounted. There we go. L equals 2. Counting's hard. See how easy it is to miscount? Thank you for catching that. Okay, we're going to see later on how we can use our periodic table to double check these rules. For now, we need to know these rules, but we're going to see that it actually makes sense, which is cool. Okay, so we have done principal quantum number, n. We have looked at azimuthal, L. And now we're going to go to our magnetic quantum number, ml. So the magnetic quantum number, why do we need another one? Well, when people were looking at the emission spectrum of hydrogen and other elements on the periodic table, they discovered that if you put these emission lines through a magnetic field, sometimes some of these lines split. This let scientists know and figure out that some orbitals had multiple orientations, meaning that if the orbital was flipped this way versus this way versus this way, it means something different. So the magnetic quantum number, ML, gives us information about the number of three-dimensional options, the number of orientations of that orbital. Now, this number does not tell us which orientation it is, but it lets us know the number of options. Okay, so this time, let's go ahead and start at n equals 3. Well, if n equals 3, that just has to be a positive integer, so it could be 1 or 2 or 3, and so on. L goes from 0 all the way to n minus 1. So if n equals 3, that's the example we're looking at, we can start at 0. There's an option, and it could be up to 1, and all the way up to n minus 1. So 3 minus 1 is 2. So the L options are 0, 1, and 2 if n equals 3. Well, 3 and 0, we count SPDF. 0 is F. That tells us we're talking about a 3s orbital. Well, how many ML, how many magnetic quantum number options are there if n equals 0 and if n equals 3 and L equals 0? Well, ML, its rules are that it can go from negative L through 0 all the way to positive L. Those are its constraints, its rules. Well, we're looking at the 3s orbital. That means L equals 0. So we can go from negative 0 through 0 to positive 0, which means 0. It only has one option. So ML equals 0. There's only one way to write that. And when we look at the 3D interpretation of S, we're going to see a sphere. Doesn't really matter which way you orient it, it still looks the same. Well, let's go up to L equals 1. If L equals 1, that means we're talking about a p orbital, a 3p orbital. Well, the number of options for the magnetic quantum number, ML, depends on what L is. If L is 1, then the magnetic quantum number can go from negative 1 through 0 to plus 1. That gives us 3 options: negative 1, 0, and plus 1. This corresponds to px, py, and pz. And we're going to talk about these visualizations in a minute. Now, we don't know if negative 1 means z and 0 means x. We don't know which one aligns with which, but we do know there are 3 options. Well, then let's go up to L equals 2. If n is 3 and L is 2, that means we're talking about SPD. We're talking about a 3D orbital. Well, ML options depend on what L is. If L is equal to 2, then ML can go negative 2, negative 1, through to 0, from plus 1 to plus 2. That gives us 5 different options. Guess how many 3D orbitals exist? 5. And we're going to learn next class about what those shapes are and what they look like in 3-dimensional space. And as we go up, as soon as you get to the F, well, lo and behold, there are 7 orientations of F orbitals. Okay, so we have now defined the different orbital options using the first 3 quantum numbers: the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. Well, in each orbital, we can have 2 electrons. But no 2 electrons can have the same 4 quantum numbers, which means their spin quantum number, the 4th quantum number, must be unique. The rules for the spin quantum number, ooh, that's a typo, it has to be plus half or minus half. Basically, it could be up spin, so if it's spinning like this, it has a moment going up, or if it spins like this, it has a moment going down. If you learn from physics with the coil thing, it shows the moment going up or the moment going down. So electrons can have an up spin or a down spin. That's it. We're going to designate it usually with a single-headed arrow, an up spin or a down spin. So when we're putting electrons in orbitals and defining where these electrons are, we can have 2 electrons with the same first 3 quantum numbers, but one is going to be up and one is going to be down. This is the Pauli exclusion principle. We've already talked about it. Every electron needs a unique set of 4 quantum numbers. The first 3 can be the same, but the second or the 4th, it could be plus half or negative half. They need to have opposite spins in the same orbital. Parallel spins, not allowed. Okay, quick recap. Chat with the person beside you. The magnetic quantum number best describes what? Chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Wow, 93%. Well done. Okay, so we have identified this as the magnetic quantum number. Otherwise, A, the shape of the orbital, which quantum number letter is telling us that? Just go ahead and shout it out. L. What about B, the energy, the big idea of the energy? N, yes. We'll see that we can have slightly different energies later on. On the pathway of the electron, none of the quantum numbers are going to tell you that. We can take the square of the wave function and find the probability of finding the electron somewhere and correlate that with energy, but we don't know if it's heading this way or that way or where it had lunch or whatever. The spin state of the electron, that is the ms. Well done. Okay, so why do we need to talk about these quantum numbers? Well, it gives us information about where the electrons are, what their energies are. We need to know this to be able to do cool chemistry. So we also need to know which of the following quantum numbers are valid, which of them are allowed, and which of them are not allowed. We talked about rules, and now we need to apply these rules. If it's allowed, we can also interpret which orbital it's talking about. So let's start with part A. These are the quantum numbers in order of first, second, third, and fourth. So for A, it's telling us that N is equal to 3, L is 1, ML is 0, and MS is plus a half. So we're going to go through these rules and see which of these are valid. Well, for the principal quantum number N, the rules are it has to be a positive integer. So it could be 1 or 2 or 3 and so on. Yeah, that looks fine to me. For L, its rules are it goes from 0 to n minus 1. N is 3, so L could be, based on n, 0 or 1 or 2. L equals 1 is one of those valid options. For ML, the magnetic quantum number, it can go from minus L through 0 up to plus L. Well, L equals 1, so ML could be -1, 0, or +1. 0 is a valid option. The spin number is given as a plus half. Sometimes we write in the plus, sometimes it's implied, whichever. Well, it's one of those two valid options, so yes, this would be a valid set of quantum numbers. Well, how do we interpret which orbital it's talking about? We look at what that principal quantum number is, and then we interpret L. We count S, P, D, F. We go S, P, we stop at 1. Therefore, it is a p orbital, a 3p orbital. Do we know if it's px, py, or pz? No, it could be any one of those. Sometimes with further information, we could narrow it down, but based on what we have, it's going to be one of them. Okay, let's jump to part C. Here, n equals 2, L equals 0, ML is also 0, MS is plus a half. Okay, so n equals 2. Sure, that meets the rules as a positive integer. Let's look at L. Does it meet the rules of 0 to n minus 1? Well, n minus 1 is 1, so it could be 0 or 1. Sure, that meets the rules. ML, we look at what L is. It's 0. It's allowed to go from -0 all the way to +0, which is 0. And it is 0. There's only one option, and it hit the one correct option. And MS is one of the two valid options. So yes, this would also be a valid set. How do we figure out what orbital it is? Well, we look at the principal quantum number. That gives us the first number. And then we interpret what L equals 0 is. SPDF, we start counting at 0 for S to S. That's it. Okay, now your turn. This is part B. Chat with the person beside you. Which orbital, if valid, do these quantum numbers communicate? Chat with the person beside you and convince them that you're right. And 10 more seconds. And 3, 2, and 1. Okay, most people going for E. We have a few votes for the middle. I agree this is not valid. Based on n equals 1, the principal quantum number is 1. L equals 1, that tells me a P, but L equals 1 breaks the rule because it can only go up to n minus 1. So 1p doesn't actually exist. So although I get 1p when I count it out, it broke the quantum number rules. So we're going to see when we look at our periodic table and when we look at atoms in real life, 1p doesn't even exist. There is no option for that. Okay, let's do the next one, part D. Which orbital corresponds to this quantum number set, if valid? Chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, most people going for A. A is correct. If you chose D, that means you started counting L at 1 rather than L at 0. So make sure you're starting with S is 0, so S, P, D, F. When you get to 3, that means it is F, and this does exist. Okay, so now let's take these rules. Who enjoyed memorizing these rules in high school? Okay, a few people did, and that's great. I didn't. I hate memorizing rules. So I try to avoid memorizing rules as often as possible. If you can come up with a rational explanation for the rule, then you don't need to memorize it. You can just think through it and come up with it when you need it. We're going to see when we're using our periodic table in a couple classes that we can derive these quantum number rules from our periodic table. We're going to be able to count across rows and columns and see how all the rules are staring at you on your periodic table, and we always give you a periodic table. So it's very helpful. We're now going to take these quantum number rules, which are important, which we do need to know how to interpret, what's allowed, what's not allowed, and now translate it into something more meaningful that we can work with. We're going to look through the different options when the quantum numbers equal whatever, when the orbitals are thus. What does it mean? So let's start at the lowest energy and the lowest quantum number. If n equals 1, what are our options? And we now know how to count that out. Well, the number of nodes is going to be 0 because the number of nodes is n minus 1. If n equals 1, what are the options for L? Well, it can go from 0 all the way up to n minus 1, which is 0. There's only one L option, which means we only have an s orbital. We do have a 1s, but we don't have a 1p, we don't have a 1d, we don't have a 1f, only one s exists. And if we only have the 1s orbital, what are the options for the magnetic quantum number? Well, there's only one option. So it's nice and simple when we're at principal quantum number 1. The only orbital option is a 1s orbital, and there's only one of them. We can compare this to looking at this standing wave. When it's anchored here and anchored here, we can see it has no nodes. We don't count the anchors as nodes. Wave functions exist in 3 dimensions, x, y, z. In your workbooks, we're only drawing it in x when we're talking about the wave functions, just so that we can keep it nice and simple. So if we're just looking along the x-axis, we could see it's nice and simple, no nodes. That could be our psi wave function. Well, we could then square that wave function, whether it's positive or negative, everything becomes positive, and we could plot out that electron density, and that gives us information about the probability of where to find that electron. I'm going to jump to these images here because it's a little more interesting. So here we have 4 different ways of talking about the 1s orbital. We can plot it out. We can draw this wave function in 1 dimension. Now, of course, we know it actually exists in 3 dimensions, but we just have the x for now. So when we draw this wave function on the x-axis, it kind of goes out away from there. When we square it, imagine we squared this number on the line and this number on the line and this number, and you can see that the numbers increase. If we multiply those by each other, they just become more amplified. This squared function here gives us the probability. Remember, we could talk about the wave function. It's a description of the electron. When we square that function, we get a probability map. We can plot it out looking at the x-axis. You can see the probability is highest when x equals 0, and x equals 0 is when we're right at the nucleus. So that electron is most likely to be found closest to the nucleus, less likely to be found as you go further away from the nucleus. We can draw this out in more dimensions by using a probability density map. I'm going to go back up to the top one here for a second. Probability means the chance of finding it somewhere close to or farther away from the nucleus. Here you can see it's kind of symmetrical, so whether we go this way or this way, the probability goes down. We can see most likely, just wait, most likely it's going to be found closer to the nucleus. Who likes to do photography in here? Does anyone have one of those cameras that's actually like big and heavy with a nice big lens? Okay, so you're familiar then with opening, the aperture, is that the right word? And you can collect a longer photo so more information comes in. Let's imagine we use that nice big expensive camera and we were looking at one atom and plotting where that electron was. We can't actually do that exactly, but let's imagine that we could. If I took a picture of where the electron was and then overlaid all those pictures, that's where this probability density map comes from. So my first picture, I find it right there where that red dot is. Second picture, third, fourth, fifth, sixth, seventh, eighth, 1,000, 10,000, so many overlays. We can see most often the electron is close to the nucleus. Less often, it's found further from the nucleus. You can see that we're getting a circle here in 2 dimensions. And if this was 3 dimensions, we would have a sphere. And so I brought a little ball here today, which represents our 1s orbital. As you go away from the nucleus, x, y, or z direction, you're less likely to find it, but it is symmetrical in all the different dimensions. This is why we don't have 1s, x, y, and z. If I rotate this sphere, it's still the same picture. Most likely, it's found closer to the nucleus. As we go out, it's less likely. So this probability density map probably gives us the best idea of where we're going to find that electron. Statistically, most often close, sometimes a little further away. We can also talk about orbitals and visualize orbitals using an isosurface. It's based on this wave function here. You can still see it's a sphere, a 3-dimensional circle, and it encapsulates where we're most likely to find that electron. The reason why we're using isosurfaces is because it's also going to capture positive and negative phase when we get there. We're going to see different colors, and that's going to help us out there. So a 1s orbital is as simple as it gets. It's just a sphere. Well, let's make it a little more interesting. Let's go up to n equals 2. What are the options? Well, if n equals 2, we know that we're going to have one node because n minus 1 is 1. So any orbital that starts with principal quantum number 2 has one node. Well, what are the L options? It could be 0, which means it's an s orbital, or it could be L equals 1, which is a p orbital. Both of them are going to have one node. Now, this picture here is 1 dimension. We need to now move to 3 dimensions. I'm going to start with L equals 0, which means I'm talking about the 2s orbital. Well, what are the ML options? It's allowed to go from 0 all the way up to L minus 1, which means it's just plain old 0. So we're back to not having to worry about multiple options in 3-dimensional space. It's just 1. There's only one 2s orbital. Now look at the blue isosurface here and compare that to the 1s orbital. Besides the color, It's basically the same shape. 1s is like this big, 2s is this big. Do you want to guess what 3s is? It's just a bigger sphere. And 4s, an even bigger sphere. If it's an s, it's going to be that spherical shape. Now it gets more interesting when we plot out this wave function. Again, we're plotting it in one dimension here along the x-axis. But now notice, I guess it's 2 dimensions, on the y-axis, we can see it has a positive phase above the line here. And then the blue part here is the negative phase below that line. When we were looking at the 1s, it was all the same phase. It was all just positive. There's only one type. But now when we're plotting the 2s, it goes below. So we have a positive phase and a negative phase. Important point. Phase does not mean charge. So we do not have a negative electron and a positive electron. We're not talking about charge. We're just talking about phase, like a wave function has positive phase and negative phase. The phases become more meaningful when we talk about bringing atoms together, because we're going to see that phases that match have a good relationship, phases that don't match do not have a good relationship, and that informs how molecules form. Okay, so we have this wave function. It has a positive phase and negative phase. When we square it, everything becomes positive. 2 times 2 is 4. Negative 2 times negative 2 is positive 4, right? So when we square something, it becomes positive. So we now have, when we square it, everything coming up above the line. Now I'm going to go back to this wave function here. I'm going to plot it out. So imagine here's the wave function. It goes like this, and it goes below into the negative region, and then it kind of comes back up. When it crosses the 0 line right there, that is a node. There's a 0% chance right here of finding an electron there. But we just said it had one node. So now I'm going to be this function over here. When I hit the 0 line, there's a 0% chance, 0 probability of finding the electron there. It's 0 over there. But when I rotate, this node here is the same as this node over here. When we rotate in 3-dimensional space, that is one node. If we look at this with our time-elapsed camera, we can see most often we're finding the electron close to the nucleus, but then there's this region of space in this probability density map where there are no electrons, and we have one node there. We've introduced the idea of 2s, but I haven't told you everything I want to tell you about 2s, but we're out of time. So when we come back next class, we're going to explore 2s and then move on to our additional orbitals. Have a great day. I will see you on Wednesday.